All right, William, can you hear me okay?
Yeah, we can hear you.
Perfect. All right, so we're gonna get started. As you probably know, the internet's been being really weird at Jerome starting yesterday. So we may freeze for a minute, but William will let me know if we get frozen and we'll go from there. So a couple quick things. So as you can imagine, I've gotten quite a few emails from students who are sick and can't make it to in-person class. And I just want to remind you that's totally fine. You don't need to email me if you're sick, if you just need to miss class. You can live stream this. So I'm live streaming this now. The live stream link is on Moodle, so you can watch it in real time from wherever you are. Or if you're too sick to watch it during real time, there's also asynchronous lectures posted on Moodle that you can watch when you're feeling better. So you really only need to notify me if your illness impacts your ability to complete an assignment, okay? I'm gonna wait 1 minute. You guys seem to be frozen, but I'm hoping you can still hear me.
Your audio, but your video.
But you could hear me?
Yeah, we could, yeah.
Okay, perfect. So all of that being said, you know, if you're not feeling well, please, please, please take care of yourself. There's so many things going on right now. You know, if you're not feeling well, make sure you're drinking fluids and getting rest, and do what you need to do to get yourself back to healthy. So I appreciate your continued masking in the class to help protect everybody. And hopefully if you're not feeling well for any reason, you're getting tested so we know if it's COVID, so you can quarantine and all those things. But do what you can to stay safe. And, you know, I will always work with you if you are sick and have to miss something. So please don't worry about that. A couple of other announcements about things coming up. So first I want to talk about the Chapter 1 quiz. So we have our first chapter quiz that's going to be on Monday. And the chapter quiz is 10 questions and they are all multiple choice. So this is sort of a longer mini quiz almost. It's the same type of material. And you'll have 1 hour once you open the quiz to complete it. So it'll be open the full 24 hours of Monday. So it'll open right at midnight and it'll close at 11:59 p.m. And you'll have to find a 1 hour period that you can take it. And you just log in, you do the 10 questions, and then you submit it just like the mini quizzes. So the best way to prepare for this chapter quiz, as I mentioned before, is to go through the Chapter 1 mini quizzes. You can go through them through the gradebook and see what you got right and wrong and what the right answer was, and make sure that you understand all of those problems. Also going through your homework to make sure that you understand those homework problems, and then just making sure that your notes are organized. So you can use your notes on the quiz. So making sure that you are able to access things and read your notes is super helpful, okay? So in terms of that, that will pop up on Moodle for you, and you'll see it. There's also a chapter review right where the test will be. It says like chapter 1 quiz, but if you open up that like drop down, you'll see that there's a chapter 1 review with some practice problems and solutions. So if you feel like you've done a lot of studying, you feel well prepared, you can certainly do that quiz and then check your answers to make sure that you're on the right track. Okay, so that's coming up on Monday. I also want to talk about a change that we are making to the mini quizzes. So starting with limits and continuity, so starting in chapter 2, for each mini quiz, you're going to have 2 attempts instead of 1. And there's a lot of sort of things that go into this. So we want you to be able to have more exposure to problems. So having 2 attempts, your questions are pulled from a pool, so you'll see more types of problems. There is a 1-hour enforcement between attempts. So if you take an attempt on Saturday at 9 a.m., you won't be able to do another attempt until Saturday at 10 a.m. So there's a 1-hour enforcement so that you're not taking them back to back, because the idea is that you would take the mini quiz, you would think about, you know, what parts you felt like you understood and things that you were like, oh, I wasn't really sure how to do that. You would review it, and then you would do a second attempt afterwards. Okay, so some important things that go with that is that your highest score is what we will keep. So there's no penalty on doing a second attempt. So if you were to get a 3 on your first attempt and a 0 on your second attempt, you would still get the 3 because it's higher. Okay, we also, for educational reasons, we are not going to show you your score after the first attempt, because we don't want you to use this just for grades. We want you to use this for learning. So we are hoping that everybody will take advantage of the second attempt each time so that they have more exposure and practice. You don't have to do a second attempt. You can just do 1 attempt if you'd like, but I strongly encourage you to use both attempts. So you'll have to make sure that you start early enough that that 1-hour period interfere. If you start your first attempt 30 minutes before the due date, you won't get to do a second attempt. Okay, so again, that's going to start with limits and continuity, which is what we're going to be talking about today. That's the quiz that's due on Sunday. So you could do an attempt tonight and then another attempt tomorrow, or you could do an attempt Saturday morning and then another one Saturday night, right? But the idea is that anything that you're unsure about from the first attempt, you want to review it in your notes, or even things you are sure about, you can go back to your notes to make sure that you're like super confident in it before you take the second attempt. Okay, so that's new. And again, that's for the mini quizzes going forward, starting in chapter 2. And again, we are going to keep the highest grade, so there's no penalty in using a second attempt. So I hope you will all take advantage of that. Okay. Let's see. So there's one more sine and cosine review this afternoon. Again, I emailed you those links and they are posted in Moodle that William will be doing today. So if you wanted some extra practice with sine and cosine, especially the graphing stuff that we did last time, feel free to drop into that session. And I will post the link to the recording afterwards if you're not able to make it. That will be posted on Moodle under the Getting Started, where I've been posting those links. Let's see, anything else? So again, we have drop-in help today, drop-in help tomorrow, drop-in help on Sunday. So if there's any questions that you're going over to practice for the chapter 1 quiz, you can feel free to ask them at drop-in help. So you can share your mini quiz as long as it's, you know, past due. So anything from chapter 1 we've already done. And we're happy to go through any of that with you if you still have questions. I think that's all the announcements. So we're gonna get ready and get started and go into what's called limits and continuity. Okay, and so I just want to preface this by saying, like, this is sort of a small stepping stone into chapter 2. So we want to really understand the idea of closeness. That's what this sort of subsection is. If you've studied limits and continuity before, if you've taken calculus before, we are not going to go into the theory and in depth of limits. We're just going to present it as a general idea. And so we're not going to be doing, you know, weeks of this. It's one lesson just to get this idea going. So if you've done this more formally and more extensively, that's totally cool, but we're not going to go to that extent because the whole point of the limits is just to get us prepped for chapter 2, which is going to use it in practice. Okay, so I'm just going to switch over to my doc cam. Ooh, move this down here. Okay, so limits and continuity are related, but they are different topics. And so we're going to start by talking about limits, and then afterwards we'll do continuity. And so when we start talking about limits, what we really want to be able to do is understand what a limit is conceptually. So we'll walk through the steps of how we do things computationally and all of that. But the big idea is just sort of understanding what they are and how we're going to be using them for our purposes. So we start with just the definition. And so the definition we're going to use is that the limit is the dependent value that a function approaches as the independent variable approaches some value of c. So what that means is as x gets close to some number, the limit is the number that y gets close to, right? The dependent value. And this is going to be important, this word close, as we go through this, because not all functions are defined everywhere. So we are not going to be able to actually plug in the number we are approaching. So we use the word close to sort of substitute for plugging in. So the notation that we use for limits is the limit as x goes to c of f of x equals L. Okay, so that's what the notation looks like. This c is the independent value we are approaching. So you might be approaching 1, you might be approaching 5, you might be approaching 10, but it means that you're approaching it on the independent axis. And our L is the dependent value that we are going to be approaching because our x value is getting close to some number. So remembering which one is which, whether dependent or independent, is going to be important. But let's see what this looks like visually. Okay, so I want to give you a visual representation of what we're talking about when I talk about getting close. So let's say we're going to consider the limit as x approaches 2 of this function right here. Okay, so we have some function f of x, and we're talking about the limit as x gets close to 2. So when I talk about getting close to 2, what I mean is that we are going to be approaching 2 from both the left and the right. And we're going to talk about what that means in a few minutes. But the idea is that you can get close to 2 from either side. And the question is, well, what does that mean in terms of this y value, right? Like as we get closer to 2, what does the y value get closer to? And you can see pretty clearly that as we get close to 2, this y value is going to get close to 4. So that means that this limit is going to be 4, right? So I keep saying close to. And so one of the things I mentioned before, but I'm going to say it again, is that we can't actually plug into, right? So we're not plugging in anything, so we don't have the function here, but we can't look at just what the value of 2 is, right? And we know it's 4 because we did functional values before, but with limits, we're saying we want to get close to. And so we're going to talk about what that means, right? Because closeness is really relative. Okay, so closeness for 2 is going to be things like 1.99. 1.99 is close to 2. Okay, 1, not that close to 2. 1 is like way over here, right? Now, 1 might be close to 2 in other things in math, but for our math, we're talking about, things like 2.001. That's pretty close to 2. So we're talking like really, really close. Okay, so we need to learn more formally how to evaluate different things and how we set this up algebraically, how we look at this graphically. But there's some more things we need to learn before we can quite do that piece. But hopefully this is giving you a visual idea of what we want to do. Okay, so let's look at another example. And this example is just meant to illustrate why we can't just plug in the number that we're interested in. Okay, so again, we're just going to look at this visually. We're not going to do anything super formally yet. Right, so the limit as x goes to 2 of f of x, right? If we just had f of x here as an algebraic function, and we said, hey, you know what, let's just plug in 2, right? And we ignored this restriction that we have to be close, we run into this problem that we would then be dividing by 0, right? And we never, ever want to divide by 0. We all know, like sort of in our soul, that that's a bad idea. And so we can't plug in 2. But does that mean that the limit doesn't exist? No, because again, if we get close to 2, but we don't plug in 2, what ends up happening over here is that we get closer and closer to the y value of 3. And you might be thinking, hey, there's a hole there. That's a problem, right? It is a problem for a lot of things, but what it's not a problem for is limits, because since we never actually plug into, we never actually fall into the hole. We get really, really close to the edge, right? 1.9, 1.99, 1.999. Those are all close. But since we never actually get to 2, then we don't fall into the hole. And so we can see that this is approaching 3. So the limit still exists, even though we can't plug the number in, okay? So limits become really important because they allow us to look at functions, even if they don't exist at that point. We can still get good information about what's happening near that point. Okay, so if we want to be able to do this formally, right? We want to be able to calculate things. We want to be able to work with functions. We have to take a step back and we have to make sure we understand when functions exist and when they don't exist, okay? And so in order for a limit to exist, when we approach whatever our value is from the left, it has to be the same as from the right. So again, like in this example, when we approach 2 from the left and the right, that ended up approaching 3, right, from both directions. They're approaching the same number. If it's not the same from the left and the right, then the limit doesn't exist and we run into trouble. And we'll look at some examples of that. But first, we want to look at some examples that do exist and understand how we use this sort of idea of limit from the left to be helpful in figuring out our limits. And so I'm not sure how well you can see this, so I'm just going to write it a little bit bigger. So this uses A instead of C, but I'll highlight the key part here. Okay, so when we talk about a limit from the right, okay, we use this plus symbol to indicate that we are doing our calculation from the right. And when I say from the right, I'm talking about using a number that is slightly bigger than the number we are approaching, right? So if we're interested in what's happening at 2, and we're approaching 2 from the right, we're using things like 2.001, so something slightly bigger, okay? When we do a limit from the left, we use this minus symbol to indicate that we're approaching it from the left. And so these are numbers that are slightly smaller. Okay, and again, this idea of big and small and closeness, we're talking about, 1/1000th away from the number we're interested in. Okay, so what does this look like in practice, right? So we're going to do one together, and we're going to do a pretty straightforward one where we'll have a good idea of what it's going to be. And then I'll give you one to try that's a little bit harder. Okay, So here we're interested in finding the limit as x approaches 3 of 9 plus x. And I know that you can just plug in a 3 here and you can get a value, but we are not allowed to do that. In order to provide the evidence for the limit, we have to approach 3 from the left and from the right. And so what we're going to do, this is from the left and this is from the right. Okay, we're going to take these values that are close to 3 from a little bit to the left. So 2.9, 2.99, 2.999. Those are numbers that are close to 3 from the left. And we're going to plug them into our function. So that's going to give us 11.9, 11.99, 11.999. Okay. And so we as mathematicians know that we are trying to figure out what we are approaching in terms of a y value. So 11.9, 11.99, those are all approaching 12 because we're adding a 9 every time we get a little bit closer. We also have to check from the right. So when we check from the right, we pick something a little bit bigger than 3. So 3.1, 3.01, 3.001. And so we get 12.1, 12.01, 12.001. And again, we put on our mathematician hats and we say, okay, what is this approaching? Well, we can see that zeros are getting filled in as we get closer. So this is also approaching 12. That's really good news for us, right? So we would say the limit as x approaches 3 from the left of 9 plus x equals the limit as x approaches 3 from the right, 9 plus x, and they both equal 12. Okay. If the limit from the left equals the limit from the right, then you can say that the limit as x approaches 3 is 12. So the only time you can say that the limit exists without a left or right qualifier is if you have shown that they are the same. Okay, so here they both approach 12, so we're allowed to say that the limit is 12. Okay, so what I want you to do is I want you to try the next one. I'll write the function a little bit bigger in case you can't see it. But we're going to look at the limit from the left of 0, from the right of 0, and see if it's the same. And our function that we're testing this on is the natural log of 2 plus x minus the natural log of 2, all divided by x. That's our function, and we're looking at what happens as we get close to 0, right? So again, I just want you to notice if you tried to plug in 0, you'd run into trouble because of the denominator, and it's not quite as intuitive to think about what it might be as we get close to 0. So we have to plug in these values. So when we get close to 0 from the right, we get things slightly bigger than 0, like 0.1, 0.01, 0.001. And when we come from the left, we have negative values because 0 is where we change signs. So I'm going to give you about 3 minutes. I want you to try to plug these values into this function and see if you can determine what we are approaching from the left and from the right. Okay, if it's the same, then you can fill in the number here. If they are different, then we would say this does not exist. Okay, so take about 3 minutes. Feel free to check in with someone near you. Any TAs there can walk around and help, and then we'll go through it together in about 3 minutes. take about 30 more seconds to finish up whatever part you're working on. All right, so when you're plugging these into your calculator, you can certainly plug in each value one by one. I do want to show you a quick shortcut for your graphing calculator. Depending on what kind you have, this will work for any TI. It will also work for a Casio, but the syntax is a little different. So if you are looking to put in a lot of numbers into the same function, you can go, I'm trying to get away from the light. You can go to the graphing function, to the y equals, and you can enter your function in there. And so I'm going to use parentheses for my numerator. So I'm going to do the natural log of 2 plus x minus the natural log of 2. And then I'm going to close the parentheses for my numerator and do divided by x. And then what you can do is you can use the table function that's over here. So it's behind this button. So I'm going to do second table. And what it allows you to do is it allows you to enter values and it plugs them all into the function you put before. So the values that we wanted to plug in here, let me move this over. We wanted to plug in like 0.1. So I would do 0.1 and hit enter. And it's going to spit out the value. And I'll do 0.01, enter. 0.001, enter, right? So it lets me enter the values and it puts them all into the same function. So it saves a little bit of time. So that is the values that I was doing, 0.1, 0.01, 0.001. Those are all values from the left. Oh, just kidding, from the right, because those are slightly bigger. So I'm just going to copy those down. So 0.4879, 0.49875, and 0.49908, right? And so I can see that those values are approaching 0.5. So my limit from the right is 0.5. I can also plug in the negative values that I'm interested in. So negative 0.1, negative 0.01, negative 0.001. And so I look at those values and I get 0.5129. And then I get 0.50125. And then I get 0.50013, right? And so again, I can see that these values are getting closer and closer to 0.5. So the limit from the left is also 0.5. And so you don't have to use this trick if you don't want to. I just find it's really helpful if I'm plugging in a lot of values into the same function, which happens a lot in chapter 2, to use this function. So again, I put the function in here in my graph, and then I went to the table and I'm able to plug values in. And the one thing that you may have to change is there's also what's called table set in here, which is this blue one over here. If your calculator is not doing what mine is, you need to go to table set and make sure that the independent one says ask. That's the one that lets you plug things in. If it says auto, it's going to pick numbers to plug in for you. Okay, so that's one way that you can plug things in. If you want, you can certainly plug things in one at a time, just like we have been doing before, but it's up to you. So here we see that the limit from the right is the same as the limit from the left. So then we can say the limit in general is 0.5. And I'll tell you that for the most part, any functions that you are doing out algebraically like this are going to be the same from the left and the right. Typically just because it's a little bit easier and we're really testing that you can sort of use the right types of values. If we're going to consider things that are not the same, we tend to do it graphically. So that's what we're going to look at next. We're going to look at a picture and we're going to see if we can talk a little bit about the limits that exist on the graph. Balanced? Okay. So I want you to think about the function that's pictured here. And there's three limits I want you to consider. So we're thinking about the limit as x goes to 1, the limit as x goes to -1, and the limit as x goes to 2. So for each of those limits, I want you to try to write down what the limit is as you approach that value from the left and the value as you approach it from the right. So you'll approach 1 from the left, so you're coming up this way. You'll approach 1 from the right, so you're up here. And you'll do that for each of these three limits. If the limit from the left is the same as the limit from the right, then you can write down that limit without that qualifier. If, however, they are different from the left and the right, then your limit does not exist in this form. So that's what we're trying to figure out here. So I'd like you to take 2 minutes, maybe 3, jot down what you think is happening from the left and the right on this picture. Okay, check in with someone next to you, see if they're getting the same thing, and then we'll go over it together. So see if you can try that one out. All right, to take about 30 more seconds to finish up whatever part you're working on. All right, so we'll just go through these in order. So we'll start by looking at the limit as x approaches 1, and we'll look at it from the right and the left. So if we're interested in approaching 1 from the right, that means we're starting with values a little bit bigger than 1. So that is going to link up to this function up here. These are the values that we're getting for values slightly bigger than 1. And you can see as we get closer and closer to 1, the y value stays constant up here at 3. So as we approach 1 from the right, the y value is approaching 3. Now, as we approach 1 from the left, we're on this trajectory here, we're on this function when we're slightly less than 1. So the y value that we're approaching from the left is going to be this y value of 1. So those are different, right? And so if the limit from the left is different than the limit from the right, we say that the general limit does not exist, right? And we can see that that happens because there's this jump that happens at 1. So they're different from the left and the right. Let's look at -1 next. So as we approach -1 from the right, we're coming up this way, and we can see that that's approaching this y value of 1 as we approach from something a little bit bigger than -1. And when we approach -1 from the left, we're coming down the same function, right? There's no jump here. And we are also approaching 1 as we come down from the left. So these are the same. So if we are the same from the left and the right, then the general limit is just whatever that number is. Okay. And then last but not least, if we approach 2 from the right, so something slightly bigger than 2, we're on this function. We're coming down this way. So this is approaching a value of 2 when we come from the right. But when we come at 2 from the left, we're on this function up here, and we can see we're approaching this value of 3. So again, if these are different, we say that the general limit does not exist. Okay, so I want you to notice that at the places where the limit did not exist were the places where we had these sort of jumps, right? That's sort of a key indicator that something wonky is happening, and we have to be really careful with what we're doing. Whereas here, there was no jump here, and so the limit did end up existing. Okay, so that's what it will look like if the limit does not exist. The next sort of process that we want to add on to this is that sometimes plugging in small numbers is kind of a pain in the butt. And sometimes it's easier to simplify our function before we plug in. So that's what this problem is getting at. So I'm just going to rewrite it because I know it's really small. So we have the limit as h goes to 0 of 2 plus h squared minus 4 divided by h. And it says, use algebra to simplify the expression, then find the limit. Okay, so what I want you to try to do here is I want you to FOIL out this first term. So 2 plus h squared is 2 plus h times 2 plus h. I want you to multiply it out and then combine any like terms in the numerator and see if there's any other algebraic simplification you can do. If you get to a point where you think there's no more simplification, then I want you to take the limit. So you'll pick numbers a little bit to the left of 0 and numbers a little bit to the right of 0. Okay, so I'm going to give you about 3 minutes to try this out. Feel free to check in with someone next to you, see what sorts of algebra you can figure out, and then we'll go through it together. All right. So let's go ahead and take a look at this. Make sure that we remember all of our algebra and then see what shakes out here. So again, we're starting with the limit as h goes to 0 of 2 plus h squared minus 4 over h. We could absolutely use a table at this point on the function as it is and get the correct answer. However, sometimes, depending on your preference, it's easier to simplify the algebra first. So that's what we're looking at here. So if you FOIL this out, the 2 plus h, it becomes 4 plus 4h plus h squared. Okay, then we still have our minus 4 from this minus 4. So we notice that we have a 4 and a minus 4. Those are going to cancel each other out, right? So those go away. And we have then the limit as h goes to 0 of 4h plus h squared over h. So I notice here that every single term has an h in it. So I went ahead and I factored out the h term in the numerator, leaving me with h times 4 plus h. The reason I wanted to do that is because then I can cancel the h that's in the numerator and in the denominator. So that leaves me finally with the limit as h goes to 0 of 4 plus h. So this is a significantly simpler form than what I started with. And so when I plug things in, I'm less likely to make an error, and I'm more likely to know what my solution is going to be, because even though I'm not supposed to plug in 0, I always do it in my head anyway, because no one tells me what to do. So it gives me sort of an insight into what that may be. So I'm going to be plugging in into 4 plus h. I want to plug in values close to 0. So remember, that's when we have things to the left and right of 0, when we have the negative and positive cases here. So this is from the right, since they're positive. So that's going to give me 4.1, 4.01, 4.001. And then over here on the left, when I plug in, that's going to give me 3.9, 3.99, 3.999. So I can see that my limit from the left and my limit from the right are both approaching 4. So what that tells me is that the limit as h approaches 0 of 2 plus h squared minus 4 over h is going to equal 4. And I was able to determine that because I simplified first. Now, again, if this stresses you out, if you are like, algebra is not my jam, I'm worried I'm going to mess something up, you can plug into this function and you will also get 4 as a result. If, however, you're like, I love algebra, right? Then this will give you a more efficient function to plug into. And if you're good at algebra, it won't take you super long to simplify. So it really is a matter of preference, right? Do you prefer to do the algebra or do you prefer to plug in to the original function? Either way, you're going to get 4, okay? But that's what that means when you're asked to simplify first. Okay, so now sort of wrapping up all of these ideas, I'm just going to give you a little quick problem I want you to think about, and hopefully you're able to figure this out based on all the things we just talked about. So I want you to look at this function, and I want you to determine for which x values do you think that the limit does not exist? Okay, so remember, it's not going to exist if the limit from the left is different than the limit from the right. So I'm just going to give you 1 minute to look at the graph and to jot down where you think the limit does not exist based on that previous work that we were doing. Okay. Finish up. All right. So hopefully, based on what we learned about the definition and the other graphical interpretations, you were saying that, hey, there's something weird happening here, and there's something weird happening here. So at x equals -1 and at x equals 1 are the two places here where we're going to run into trouble, right, in terms of the limits, because here the function changes from the left of 1 to the right of 1. We have 2 different functions. Same thing over here. So hopefully you start to recognize that on a graph when you're working with limits, because that will be helpful in figuring out some future things that we talk about. Okay, so now we're going to switch gears and we're going to start talking about continuity. So continuity is related, okay, to limits. And so we had to do the limits first so that we could talk about continuity. But you've probably heard this word before at some point in your mathematical career. Now, you may not remember exactly what it is, but hopefully we can bring back some memories. So most people hear either the word continuity or the word continuous. Okay, so these mean the same type of thing. So a function is said to be continuous if there's no breaks, jumps, or holes on the interval being considered. Okay, so typically you'll learn something like if you can draw the picture without lifting your pencil off the paper, right? So that's a good way to think about it. So we end up with what's called discontinuities when we have holes or breaks or jumps. So I want you to think about the problem we just did, right, where the limit did not exist. It did not exist because we had breaks and jumps, right? So this is related to continuity. Continuity also doesn't exist when we have breaks and jumps. So the definition for continuity, we say a function is continuous at a point C if the function is defined at C. So that means you can plug the number right into the function, and the limit as x goes to C of f of x equals f of c. So what that means is if you were to take the limit of the function to that point, that it is the same value as if you plugged that point into the function. Okay, so we want to try to use this definition to show that f of x equals 3x squared is continuous at x equals 1. Okay, so I'm going to write this a little bit bigger. Okay, so what I need you to do is I need you to determine the limit as x goes to 1 of 3x squared. Okay, so you'll have to do it from the left and the right. I also need you to consider the value of f of 1. Figure out what that is. If they are the same, the limit and the value, then we are continuous. Okay, so I'm going to give you 2 minutes, since we've done a couple of these now. You want to find the limit from the left and the limit from the right. You also want to plug the value in and make sure that those are all the same. Okay, so take 2 or 3 minutes and then we'll go through it. Okay, so take about 30 more seconds. All right, so if we consider the limit as x approaches 1 from the left, so value slightly smaller than 1, we're going to use 0.9, 0.99, 0.999, right? We could keep going, 0.9999. But those are values that are all close to 1 from the left. And we get y values of 2.43, 2.94, 2.99. We can see that these are getting closer and closer to 3. Similarly, if we pick values slightly bigger than 1, we get outputs 3.63, 3.0603, 3.006. So these are also approaching 3. Since the left and the right are the same, we know that the limit is 3. That's what we were doing before. In order for this to be continuous, we also need the functional value to be the same. So that means we're taking in that 1 and we're going to plug it into our function. So 3 times 1 squared equals 3. So adding this on, since this is the same as the limit, we have shown that this is continuous. Okay, so that is the formal way that we show continuity, which is why we need to do limits first, right? Because we need to know how limits work. However, in math, the way math works is that you do a whole bunch of problems and you look at different types of functions and you start to notice patterns. And you're like, hey, every time I do this for a polynomial, this happens. Or every time I do this for an exponential function, this other thing happens. And from that, we're able to get either generalities or formulas. So it turns out, in terms of continuity, there's some cool things that happen. Okay. And that there are a lot of different functions that are continuous wherever they are defined. Okay, and we're going to talk about what that means in a second, wherever they are defined. But the functions that we study in this class, which are polynomials, exponentials, sine and cosine, also the natural logarithm, I don't know why I didn't list that, they're all continuous wherever they are defined. Okay, so what that means is if we can figure out where it's defined, and we'll talk in a second about what that means, then we'll know where it is and is not continuous without having to do the limits, okay? And so when we say wherever they are defined, this is talking about the domain, okay? The domain tells us where a function is defined. So for example, right, x cubed, the domain of x cubed is all real numbers, right? You can plug whatever you want into x cubed, no problems. That means that we are continuous from negative infinity to infinity, okay? Similarly, let's pick one that's not everywhere. Let's talk about the natural log of x. The natural log of x, the domain is 0 to infinity, not including 0, right? We use the open parentheses, which means that the natural log of x is continuous from 0 to infinity, not including 0. So if we can determine the domain of the function, that will also help us understand where it is not continuous. Okay, so let's look at example 2. I want you to figure out where this function is and is not continuous. And so I'll write this a little bit bigger. This is 2 divided by x minus 4. Okay, so if you are trying to think about where this is and is not continuous, I want you to jot down where you think it is and is not continuous based on thinking about the domain of this function. And we can think about it in this way because this is a rational function, which is a polynomial over a polynomial. Okay, so take 1 minute to jot down your thoughts here. Okay, so if I'm thinking about the domain, there's sort of 2 key ways I could write this. I could say x goes from negative infinity until 4, open bracket, not including 4, and 4 to infinity, right? So those are open brackets. And remember, sometimes we use this symbol to say it belongs to. Or I could say something like x cannot equal 4, okay? So that tells me where it is continuous. I'm continuous from negative infinity to 4, or from 4 to infinity without including 4. Or I could use the language, this function is discontinuous at 4. So if something is not continuous, we say it's discontinuous. But that's what we're looking at here. We use the domain to talk about the continuity of most of the functions we look at. Okay, so let's think about the next sort of situation we might find ourselves in. So here we have a piecewise function. I'm going to write it just a little bit bigger. So we have x squared minus 4 for x less than 0, and x minus 4 for x greater than or equal to 0. Okay, so the first thing I notice is that both pieces of my function are polynomials, which means that by itself, both of them are continuous. So x squared minus 4 is continuous everywhere because I can plug whatever I want into it. And x minus 4 is continuous everywhere by itself, right? So initially I think, oh, good. Both of these individually don't have any big problems. So what I need to figure out here is if the function jumps, right? Because there's a difference between what's happening at 0. That's the point I'm concerned about here, because that's where the function changes. So there's 2 ways to do this. I can do the limit from the left and the right to see if they're the same, but I can also just check the functional value because these are polynomials, which means if I were to plug a 0 in here and a 0 in here, I would like to see the same functional value to make sure that they didn't jump, right? So when we have a jump, they're going to have likely different values. So if I were to do a quick gut check, I plug in a 0 here, I get -4. I plug in 0 here, I get -4. So I'm pretty confident that both of those are going to reach that -4 and not have a jump. Okay, so since they are the same, I'm pretty confident that this is continuous everywhere. Okay. If I was doing this really formally, I would use the limit from the left and the right. But using that, I can then also double check to make sure that I'm right by graphing this, right? I can look at x squared minus 4 and x minus 4 and make sure they connect. But typically this is enough for what we're doing. Okay. So finally, the last thing we want to be able to do is think about real world situations and think about how that would be either continuous or not continuous. And so I want you to consider this situation here where we are in a parking garage, okay? And any fraction of the first hour is $8. So what that means is you drive in, it costs you $8. And if you stay for 10 minutes, 15 minutes, 30 minutes, it's $8, right? The whole entire first hour. It doesn't matter whether you stay 10 minutes or 45 minutes, it's $8. As soon as you go into the second hour, okay, so at 61 minutes, you start your next $8. So now it's $16, right? $8 for the first hour and $16 for the second hour. And it doesn't matter whether you stay 61 minutes, 65 minutes, it's all $16 until you hit the third hour, and then it jumps up again, okay? So what I want you to do is think about how you would talk about the continuity of this function. So what I would like you to do is I would like you to try to graph what this might look like, and then think about what you would say about where this function is and is not continuous, okay? So I'm gonna give you 2-3 minutes because I want you to graph it. Feel free to check in with someone next to you, and then we'll go through it together. Okay, take about 30 more seconds to finish up whatever you're working on. All right. So if we were going to try to draw this, right, the time would be along the bottom axis and the dollars would be around the up and down axis, right? So it's important to understand which is our dependent and independent variable. For the first 1 hour, it doesn't matter whether you stay for a few minutes or a lot of minutes within the hour, it's going to cost you $8. And so from the moment you arrive until exactly the 1 hour mark, it's $8. Okay. As soon as you go 1 minute over 1 hour, okay, it jumps up and now you're in the second hour. And that whole time, your total cost is $16 because it's $8 for the first hour and another $8 for the entire second hour. But again, it doesn't matter if you're only there for 1 hour and 10 minutes or 1 hour and 45 minutes. It's the flat fee for that entire hour. And then at 2 hours, right, as soon as we go over that, we jump into the next pay category, right, which is $24. So this creates what's called a step function, okay? And it would just keep going, right? So like after that, this isn't even on my axis, but like we would have an open circle and this would go here and it would be $32, right? So it would just keep going in terms of every hour, we bump up another $8. So what does that mean in terms of continuity, okay? So the problem happens right at that hour mark, right, where we change over. So otherwise, we're continuous. We're continuous from 0 up until we get to 1. And then we have a problem at 1. But then we're continuous between 1 and 2. But then at 2, we jump again. So this is continuous except for on the hour mark, right? So 1 hour, 2 hour, 3 hour, 4 hour. We're not continuous there because our function changes, right? It jumps, but it is continuous in between. So if we're talking about this, we would talk about the discontinuities. We would say something like, we have discontinuities on the hour or at 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, so on and so forth, right? And again, part of what we're doing is trying to predict what will happen later. So even though I only gave you information about the first 3 hours, you could easily tell me that there's a discontinuity at 5 and at 6 and at 7, because we know that the money keeps adding, right? And that on the hour, we're always going to have this same issue. Okay, so that's how we talk about this scenario. In general, if you're asked to talk about continuity from a word problem, I strongly encourage you to graph it because it helps you sort of visualize and see where the problems exist. Okay, so that is the end of continuity. We don't have enough time to start the next section, so we will stop here. So on Tuesday, we'll pick up with 2.1. Please stop by drop-in hours if you have questions preparing for the quiz. Otherwise, have a nice weekend.